Okay, so like I said, if you have any questions as I'm discussing, I'll put those in the chat box, and then I'll try to address those at the end. But for the sake of time, I'm going to get started. And we're going to talk about some of the earlier topics from part one first. Right. Let's start off with the physics of blood flow. This was part one. And just some of the, principles, equations, topics that you should recall from this topic. So first off, our general equation, right? Pressure gradient, which is delta P, is equal to flow times resistance. And this equation we said is true for any liquid in a tube, right? Any liquid in a tube. But as far as converting this to our physiology, the equation we want to recall is going to be mean arterial pressure. And another way to express this is our driving force. This is the force pushing blood through our vasculature. So the driving force is equal to cardiac output times total peripheral resistance. And then again, this is more relevant to our physiology. So this is the equation that you definitely want to recall, but this is how we kind of got there, right? The same principles that apply to any liquid in a tube also apply to our blood in our vessels. We also want to think about the relationship between resistance and other various factors. So resistance, this is basically any obstruction to flow, right? Any obstruction, any hindrance to flow. And so as we see resistance increase, a couple things we can equate to that. We can draw a parallel. So increased resistance is going to be seen when there's increase in the length of the vessel. Sorry, length of the vessel, right? So as the length of the vessel increases, resistance goes up. As the radius goes down, as we have a decrease in the radius of the vessel, the resistance goes up. Okay, smaller radius, smaller diameter, the increased resistance. And then viscosity was the other one. So increased viscosity of the blood would also increase your resistance, okay? Now, another thing that we can equate this to is flow. So as resistance goes up, flow goes down, and all of these things are going to be true as well. So increased resistance, decreased flow happens with all three of these factors. All right, the third sort of important factor here was just thinking about the difference between our driving force and resistance in the systemic versus the pulmonary circulation, right? And how those are different but end up being equal in terms of flow. So in our systemic circulation, when we have an increased pressure gradient or increased driving force, we're going to see that that results in so increased driving force is a bigger differential in our systemic circulation. So the pressure in our arteries compared to the pressure in our veins, we have a bigger gradient between those two. So there's more resistance, but there's more flow, but there's also more resistance, right? Greater driving force, but also a greater resistance. In the pulmonary circulation, You kind of see the same thing, but there's less of a driving force, also less resistance, smaller distance, right? And so both of these equate to the same thing, equal flow. So just kind of comparing the pressure gradient and the amount of resistance in both of our vasculature assist circuits, so the systemic circuit, the pulmonary circuit, but how together they sort of equate to the same flow rate because the resistance and pressure gradient are different. So these are important principles you want to recall and be able to apply to your questions when they come up on these topics. Again, you should recall this equation more closely and be able to apply it. And then specifically how resistance and flow change when these factors change: the length of the vessel, the radius, and the viscosity. Okay, all right. Let's keep going. We're going to move on to speak about our capillaries. All right. So now we're going to move on to talk about flow to capillaries. Okay. And two things here. One, we want to think about the various structures that regulate flow to the capillary beds. Okay. So we want to remind ourselves we have a couple different factors in different locations that are going to regulate flow. So in our arterioles, we have some features, some properties. We have the precapillary sphincters, and then we have the meta-arteriole. And so what are the changes that would increase, that would cause vasoconstriction or that would cause vasodilation? So when each of these structures constrict, which of them would cause vasoconstriction and vasodilation towards the capillary bed? So always think about how much flow is going towards the capillary bed. So when we have decreased contraction of the arterioles, right, we want to say relaxation of the arterioles here or decreased contraction. That's going to cause vasoconstriction, all right? For the precapillary sphincters, we're also going to decrease contraction to cause vasoconstriction. And then for the meta-arterioles, because this is going bypassing the capillary bed, whenever we vasoconstrict the meta-arterioles, that is actually going to cause more flow to the capillary bed. So whenever we have increased contraction, that's going to cause more flow to the capillary bed. That's seen with vasoconstriction. And then the opposite is true. For vasodilation, we're going to have increase the arterioles, increase the precapillary sphincters, and then decrease the meta-arterial flow, right? So just looking at the relationships between these three components of the capillary beds and how we can increase flow, or in the case of the meta-arteriole, increasing flow actually bypasses that bed. It goes right from the arteriole to the venule, bypassing the capillary bed. So this is always going to be different than the other two factors. All right, let's talk about the Starling's forces. With yourself. And you should go over all of these features. You should be able to identify them on an image, but also just identify them if they're being described in a question. Let's talk about the Starling's forces. So with Starling forces, we have our hydrostatic force, which is a push. And then we have our osmotic oncotic force, which we said is a pull. And then in terms of thinking about the change in pressure, we're going to see that the hydrostatic capillary force, right? The capillary hydrostatic force, that is going to decrease from the arterial end to the venial end. Okay, if you go back to that scenario that we talked about, we look at the pressures on the arterial side, pressures on the venial side, and what we see is that the capillary hydrostatic force decreases from one end to the other. So that is part of the change that results in overall filtration happening at the arterial end and then reabsorption happening down at the venial end, okay? We also want to remember another important factor that's going to help you with these questions is that the interstitial fluid oncotic force is usually zero, right? This should usually be zero. So definitely watch out for this, which means that there should be no proteins. There should be no proteins in your interstitial fluid space. Okay, this is where we begin to get things like edema. If we do have proteins entering that space, as they're going to exert an oncotic pull to draw more fluids from the capillary into the ISF space, okay? But this should normally be zero. So just watch out for that. And so when you think about the net movement, that's going to be relative to the capillary. Always think about your push and pull as relative to the capillary. Okay, so net movement is relative to the capillary, right? That is to say that filtration is fluid moving out. Let's put that here. So filtration fluid moves out of the capillary. An example of this is if your capillary hydrostatic pressure, let's say that was equal to 40, and your interstitial fluid, interstitial fluid oncotic pressure was equal to 10. So this creates the filtration force, right? So this is going to be 30 in our example. On the other end, our absorption is when fluid moves into the capillary and to again give those forces. Remember that capillary, hydrostatic, and the interstitial fluid oncotic are both filtration forces. So definitely have sort of like a little cheat sheet. You can write this down right on your exam. I'll write this down on scratch paper so that you can remember which forces are associated with filtration, which are for absorption, and then you can just plug your numbers in, very easily. So the interstitial fluid hydrostatic pressure, this is one of the forces favoring absorption. Let's say that was 15 in our example here, while your capillary oncotic pressure is equal to 15 in our example, right? So our total absorption force would be equal to 0. I'm sorry, this would be equal to 30. I'm sorry. This would be 30 as well. And this up here, let's correct this, this would be 50. Right, so we just add these together. So combining our filtration forces, 50 millimeters of mercury, combining our absorption forces, 30 millimeters of mercury. So our overall force, first of all, favors filtration, which is the greater force, and then the total direction would be out of the capillary, and the value of that would be 20 millimeters of mercury. 20. So this is how you should be able to calculate when you get to these questions. So when you get to your filtration forces, absorption forces, then you simply plug those in, and then your net filtration pressure is going to be equal to 20. With this. All right. And overall favoring filtration. Okay. So this is what you should recall from your capillary hydrostatic force. Um, Again, be able to apply this to questions, either written questions or more calculation type questions when you see those on your test.